Good afternoon, gentlemen, and welcome back to part 2 of our sodium formate reduction from a silver nitrate solution. It's probably been about 2 or 3 weeks since I filmed the first segment. I've got everything set up in front of me that we're going to use for our experiment. And over here in our fume hood, what we have over here is our solution that we started with in the first part of the video series. And what that is some silver and some copper dissolved in nitric acid that was recovered from one of my final steps of cementation that I do from the silver cell process. So inside that beaker is probably 80% silver, 20% copper. It's a little more trashier than sterling silver as far as the copper content, but I really wanted to see just how well this selective reduction method works for this. And it's been a couple of weeks since I finished this up. Now, once I dissolved all my materials from the first video, I filtered this, and this has been just sitting in a beaker now for about 2 weeks, 3 weeks, something like that. And on the very top, I noticed that I had this spongy mass form. There's not a lot of it, and I actually set it back on the hot plate here because I wanted to warm it up to see if any of that would go back into solution. This beaker has been sitting out in my lab where there's no heat at, and the temperature has dropped down to 30 or 40 degrees on a couple of nights. And what happens is the colder this is, the less solubility you have in this solution for metals. So that could be metals, that could be a lot of things. And I filtered this solution very good. I triple filtered this solution to make sure it was good and clean. And from it setting over a period of time, if you will notice, we have some sediment in the bottom. And that is almost like a fine, powdery, clay-like substance. I'm not sure what that is, but at this step it's not going to matter, because the next thing we're going to do is add our sodium hydroxide solution to this to raise the pH. By raising the pH, we're going to precipitate out some of the metals or some of the copper that's in the solution. And as them metals fall out as hydroxide, we're going to filter this again before we add our sodium formate to drop our silver. So what we're actually doing is we're cleaning this solution up, and then we're going to use a selective precipitating agent. The selective precipitating agent will be the sodium formate. It will only reduce the silver that's in the solution. It will not reduce the copper. Now, when I do gold refining, we use sodium metabisulfite to reduce the gold that's in the chloride solution. But what happens is if you use too much SMB, it will also cause copper to precipitate out of the solution. This won't do that. Sodium formate, even if you use it in a little bit of excess, which it actually calls for a 10% excess, you've not got the chance of precipitating any of this copper out of the solution. So the first thing we're going to do is add some 30% sodium hydroxide solution to this to precipitate out some of the metals as a hydroxide. And by adding more water with the sodium hydroxide, we're going to dilute this solution, and the solubilities of them metals in a dilute solution is less than what it is in a concentrated solution. Now, if you look, there is almost 1,000 milliliters of solution here. We're going to be adding our sodium formate solution as well as our sodium hydroxide solution. So the volume of this solution is going to grow. But what I've done over here is I have a 2,000 milliliter beaker set up, And once I warm this up, I'm going to warm it up to room temperature, because if I get it real hot, of course I could get all these metals to go back in the solution. But then whenever it cools off, all the metals are going to precipitate out. So what we're trying to do here is add sodium hydroxide to precipitate out any metals is a hydroxide. Well, there's already some trash in the bottom, so it's not going to matter if we add a little bit more trash to it, because we're going to filter in the next step. So I'm going to warm this up to room temperature, because that's the temperature that I want it to be at for the most metals to precipitate out of this solution. So as soon as I get this up to about 72 degrees, I'm going to pour it over into the 2,000 milliliter beaker, and then that is where we're going to start adding our sodium hydroxide, and then we're eventually going to add our sodium formate after we do our filtering step. Okay, back over here I have us a little display set up, and each one has a reference card, and I'm going to explain to you what we have laid out here in front of us. And one of the first things I want to explain to you, if you've seen my silver nitrate videos and my silver cell videos, you'll notice that I work with my bare hands a lot of time. Well, this is not one of them instances where I'm going to do that, nor am I going to work without eye protection. Now, it's not the sodium formate that I'm scared of. It's not the formic acid that I'm scared of. And you need to go read the MSDS on both of these products to make sure the toxicology of them and to understand the proper safety and handling precautions. Now, the thing that I'm scared of is sodium hydroxide. And the reason that I'm scared of sodium hydroxide is acids attack metals. Bases attack organics. Well, your skin happens to be organic. It's not a metal. So as much as we like to be scared of acids, and you've seen on TV where the bad man throws the acid in a person's face and their skin melts off, acids won't attack flesh near as quick as sodium hydroxide does. And sodium hydroxide, we're going to have to heat this up to dissolve our sodium hydroxide into our solution. And hot sodium hydroxide is not something you want on your skin, and you definitely don't want it in your eye. If you have a splash of acid in your eye, the cornea of your eye will repair itself most times. If you have a splash of this hot sodium hydroxide hit the cornea of your eye, it will kill the tissue in that specific part of the cornea of that eye, and it will not regenerate itself. So do not take the sodium hydroxide lightly. To me, it's the part of the step that scares me the most. But like anything, you have to respect it and use the proper handling and safety precautions, and you'll come out just fine. Now, something else. Hospitals, veterinarian places that dispose of organic waste like human body parts, or when they euthanize a dog, they used to use incinerators to incinerate the parts of the animals or the human organs that they removed. Well, now with the EPA laws and everything, they don't do that. There's actually a design for a system out there. It's a stainless steel vat, a pressurized chamber. They put these the organic material inside of the pressurized chamber, and they add sodium hydroxide to it, and they raise the temperature. And what that sodium hydroxide does is it liquefies the body parts or the remains, and it liquefies them, and it's in such an environmental friendly way that they actually discharge the waste most times to a municipal waste waste facility. So, in other words, they're dissolving human body parts and flushing them down the drain using the sodium hydroxide technology, and kind of what I just explained to you about the difference between acids and metals and bases in organic material. Now, you'll see here in front of me that I have a beaker of water with this sodium hydroxide. And what we have is sodium hydroxide over here in a beaker. And we have the exact amount that we're going to need to make up our solution. But sodium hydroxide will dissolve glass. You cannot do this in glass, but what you can do it in is stainless steel. Sodium hydroxide will not harm stainless steel. So I'm going to pour this water from this beaker over into this. It's a milkshake cup is what it is. It holds 1,000 milliliters of water. There's 800 milliliters in that beaker. Now first I'm going to pour the water over into stainless and add the sodium hydroxide. Sodium hydroxide will generate a lot of heat on its own, just like adding sulfuric acid and water. So what we're going to do is we're going to pour the water into the stainless mixer. We're going to add the sodium hydroxide, and then we're going to raise the heat and allow it to dissolve into solution and cool back off. And what we have here in front of us is a little chart that's going to explain what I'm doing and how we're using this. Now, we need a 30% solution of sodium hydroxide. And what that means is that's 30 grams dissolved in 100 milliliters of water. So, to make 800 milliliters of solution, we multiply 30 grams by 800 milliliters, and we need 240 grams of sodium hydroxide dissolved into 800 milliliters of water to equal a 30% solution. Now, just for reference, at the bottom I have a number. That's 455 grams equals, or excuse me, 454 grams equals 1 pound. So, we can see that this is going to probably take a little over about a half a pound of sodium hydroxide. Now, it's going to take near all of this sodium hydroxide that I'm mixing up. But the good thing about this and the sodium formate is if you mix up a large solution, you could store this in 3-liter Mountain Dew bottles, 3-liter Pepsi bottles. Any of those will hold these solutions. So what I'm going to do is make up an excess solution, because later on I'm going to perform some other experiments that I have in mind using this same system. So there's no use making up all these small amounts when I could just make it up at one time and pour it into a 2-liter bottle and just save it for later. So, and back here you'll notice that is a 200 milliliter beaker, and those are food grade sodium hydroxide prills that we have in there. We're going to dissolve that into 800 milliliters of water, and that'll give us a 30% solution of sodium hydroxide. Now, how much do we use? We don't know. That's what our pH meter is for in the back. I've already set up our pH meter. I have calibrated it, and it is sitting just in tap water waiting to be used. So, as you can see, we're going to dissolve this into that. And the reason I'm showing you what the volume size of it is when we move over here to the sodium formate, I want you to notice how much sodium formate I have for the same 800 milliliters of water, which tells me that this is very soluble in water. And this is sodium formate. This is formic acid. We're going to use the formic acid to adjust the pH of our sodium formate solution before we precipitate our silver nitrate with it. Now this is the same thing as this, except it has sodium added in a chemical process, and you come up with sodium formate. So, we'll look down here. Now, remember, this is going to be at room temperature, and this is going to be at room temperature. So room temperature is going to dictate our solubility of our sodium formate in our solution. Now, I could force a whole lot more sodium formate into this volume of water, but upon cooling, the excess is going to precipitate out. It is just wasted product. So we have to use these numbers to give us a starting point right here. And we see that the solubility of sodium formate in water at room temperature, or about 68 degrees, is 97 grams per 100 milliliters. And what we're looking for here is a saturated solution of sodium formate. So, to make an 800 milliliter solution of sodium formate, we multiply 97 grams per 100 milliliters times the 800 milliliters we need, and that's 776 grams. Now, for reference, 454 grams is a pound. So this is about 1 3/4 pounds of sodium formate that will dissolve into this 800 milliliters of water. Okay, over here I have some notes as far as the process. This is just my personal notes. Now, something I want to point out, in my spray bottle back here, I have distilled water. In these beakers is distilled water. You don't want to use anything but distilled water in this application. Now, back over here for a moment, and something I need to touch on. Now, when I dissolve this, there's an excess of nitric acid in there. Now, normally if we was using the cementation process and we was trying to put copper in there to separate our silver from the solution, what would happen with that excess nitric a lot of times is it starts consuming copper. It has to consume copper to use the excess nitric before any silver starts precipitating from this solution. So you have to get rid of the excess oxidizer. And a lot of times when you have excess oxidizer and you try to use the cementation process, what winds up happening is you wind up with a lot of copper oxide in your product, and it's a trashier product. Now, of course, that's separated with the silver cell, but there again, you don't want to introduce more copper into the silver cell than you have to, because it depletes your electrolyte solution. So, excess nitric acid is a bad thing in the cementation process. But in this process, if we use an excess nitric acid, we're going to displace that with sodium hydroxide. We're going to kill off that excess nitric acid. So in this process, if you use any excess nitric acid, it shouldn't hurt you as bad as in the cementation process. It may cost you more sodium hydroxide to neutralize that excess nitric acid, but the impact ain't as great as in the cementation process. Now, later on, I'm going to explain to you how we figure out how much sodium formate we add. I don't know how much silver's in that solution right now, so how on earth could I possibly calculate how much sodium formate it's going to take? Now, from a scientific standpoint, we understand that 1 gram of sodium formate will precipitate about 2.9 grams of silver. Well, that's great if you know how much silver's sitting in front of that beaker in there, but we don't know that. So there's ways that we can test that. What we're going to do is we're going to add sodium formate and reduce the silver, and we're going to periodically check that till we find out that there's no more silver in that solution. And we have a test for that. And it's just a chloride test is what it is. We will add sodium formate to the beaker to reduce the silver nitrate to metallic silver. when we think that we're close to depleting the silver from the solution, we'll take a sample of that, put it in a test tube or on a watch glass, and we'll add some chlorides to it. That could be salt dissolved in water. That could be hydrochloric acid. There's all types of different ways that you could add chlorides to it. And what that'll do is, if we see any chlorides in the solution, then we know that we still have silver in our silver nitrate solution, and we need to add more sodium formate to reduce that. Now, there'll come a point whenever our solution starts testing negative for silver. Then we'll know that we're done. Until then, we'll add sodium formate to reduce it. And like I said before, with the sodium formate being a selective reducing agent, if we use it in excess, we don't risk the chance of dragging down copper. The only thing we should really be concerned with is our washing procedure after precipitation. That will be a very important step to remove any of the contaminants that may still be left in this solution. Now, I think I've pretty much covered everything for now. What I'm going to do is I'm going to go ahead and cut away, and I'm going to transfer this beaker over into our 2,000 milliliter beaker. I'm going to go ahead and take these and add them to their respective container here. And I'm going to go ahead and I'm going to start heating these up and dissolving them. And I'm going to cut away for a minute. And once I get all this set up on the hot plates, we'll come back and we'll check in periodically to see how everything's going. Now, after I dissolve the sodium hydroxide into this solution and it cools off, I could put it back in my glass beaker. That won't be a problem. You just don't want to heat it at an elevated temperature because it will etch the glass and eat the glass. So once that we've dissolved all of our sodium hydroxide and added it back to a glass beaker, then we can take and measure it out and add it to our silver nitrate solution over here to start precipitating everything as oxides. So, I'm going to cut away now and I'm going to get everything set up, and then we're going to come back and we won't have to filter this solution here because remember, our silver nitrate solution already has some trash in the bottom, so if we have any trash in this, it's not really going to matter. What's going to matter is on the sodium formate reduction. After we add the sodium hydroxide, precipitate the hydroxides, we're going to filter again to get us a nice clean solution. And then we're going to add our sodium formate. So after I dissolve the sodium formate into this solution, I'm going to let it cool off to room temperature, which our solubility says we shouldn't have a problem with any crystallization. Once it cools off, I'm going to add formic acid to it to adjust the pH. Then I'm going to filter this and get it ready in preparation for adding to our silver nitrate solution over here to precipitate our silver. And once I finish these processes, I'm going to send these samples out and have them tested for purity. That way I could perfect this process later in the future. I could do all this educational series that I want to, but I have to make sure, using parameters, that the system that I'm using is producing a pure material. If it's not, then there's no use in me using this system. There's no benefit to this system over the silver cell. In some instances there is, but you cannot process silver cheaper to purify it than you can electrolytically. The cost per ounce processed is ridiculously low. Now this process here affords you several different things that you could use according to what material you're trying to process. But the number one thing is speed. This is not like cementation, and this is not like the silver cell. This should be a fast, accurate, quality product that we're going to produce. But I've never done this experiment before either, so that's the whole purpose of doing it. Then we're going to test it and we're going to see if it'll work. So I'm going to cut away now, and I'll get back to you gentlemen in just a few minutes.